Today we're going to be looking at Intro to Systems of Equations. And our objective today is, it's kind of a long one, given a system of linear equations on a graph, we'll talk about what that means, a system. I can correctly choose the total number of solutions, either 0, 1, or infinity, and write one solution if it exists, in 4 out of 5 problems. So to get started today, tell me everything you can think of about linear equations. Now obviously this is a video, so you can't tell me directly, but think to yourself, what do I know about linear equations? What are some things that we've talked about before? What does a graph of a linear equation look like? What does the word linear mean? Well, linear means a line, so this is going to be a graph of a line. And when we talk about lines in math, we mean straight lines. So if we were to graph a linear equation, say those are axes, it would look something like this, a straight line, at least as straight as I can draw it freehand. What are some other things maybe you remember about linear equations? What about an equation? Do we have an equation form of a linear line? What does the equation of this graph look like? So it looked like y equals mx plus b. We called that slope-intercept form, which also means there are a couple other features that were necessary to write that equation. We have the slope, which is described by the rise over the run. And then we also had the y-intercept. That's where the graph crosses the y-axis, right here. We also had an x-intercept a lot of the time that we could define. It's also right here. What about sequences? Think way, way back to Unit 1, the very beginning of the year. What kind of sequence made a straight line? What kind of sequence is associated with linear equations? Was it arithmetic or geometric? These are arithmetic sequences, or arithmetic sequences are linear, more specifically. And we'll remember that arithmetic we added at each step, added or subtracted. Is there anything else you can think of about linear equations? Anything else you can remember? Okay, well that's great. That's a lot of great information, things about lines and sequences. Oh, I have another one I just remembered. There's continuity, which isn't specific to linear equations, but it is something related to them. Remember, we had this discrete idea. Lines can be dotted or they can be continuous. They still go forever in both directions. So these are all great ideas about linear equations. So let's take a look at a line now. A line on a graph, and let's talk about a couple of these features. First off, what is the slope of this line? How do we calculate the slope? Well, we have 2 points marked on this line, and we defined slope as the rise over the run. So to get from this point to this point, we need to go up and over. We need to figure out how much to go up and over. So we go up. Looks like we went up 1, because we just counted one block, 1. And now we're going to go to the right. Looks like we went over 1, 2. So our run is 2. So in this case, our rise is 1. We went up 1. We ran 2 over 2. So our slope is 1/2. Now the next question asks, what are the intercepts? Intercepts are where it crosses the axes. Remember we had y to the sky. That's how we remember that axis. Y to the sky, x goes across. And we just need to find where this line crosses these axes now. Looks like x crosses at -2. Another way you might write that is with the full coordinate pair, which would be -2, 0, because our x coordinate is first and then our y. For our y-intercept, we do the same thing. We just need to find where it crosses the y-axis, which is right here. The value there is 1. We may also write this as a coordinate pair. Now, the x value here, left and right, this is going to be 0, and then we go up 1. So our x is 0, our y is 1. And we said to write the equation we need two things. We need the slope and we need the y-intercept. Well, we got the slope up here, that's 1/2. And we got the y-intercept right here, that's 1. And now we can just plug those values into our equation, y equals mx plus b. So y equals, 1/2 goes in for m, 1/2 x, and then 1 goes in for b. So that is our equation right there. Y equals 1/2 x plus 1 is the equation of this line. Now let's just talk conceptually about lines for a minute and what we mean by points on a line. What do these points even mean? So we have an equation up here. We've graphed it the same way we just talked about. We did slope-intercept form. And we're pointing out this point here, 2, 3, falls on this line. Point 2, 3 is on this line. So what does that mean exactly? How does this point, how do these numbers relate to this equation? Well, we can take these numbers, and they represent a coordinate pair, right? This is an x value, and this is a y value. And notice we have x and y up here. We can take these and plug them in. That one goes in for x, that one goes in for y, and we should get a true statement. Should we try it and see if it works? See, we're going to put 3 in for y, so that goes up here, 3. And then we get 1/2 times x, so 1/2 times, we're putting 2 in for x, and then plus 2. So if we simplify that, let's see, the 3 comes down. 1/2 times 2 is 1, plus 2 comes down. So 3 equals 1 plus 2, that's true. That is accurate. So this produced a true statement. So how does this point relate to the equation? It's a solution. It's what we call a solution to the equation because it produces a true statement when we substitute. So our next question is, how many solutions does this equation have? So this one we said is a solution, 2, 3. Let's see, here's another point on the line. That one is 0, 2. That should also be a solution. This point on the line should be a solution. This point should be all of the places where it crosses. How about the places in between though? How about just in the middle of this square? Is that a solution? That point on the line? Or how about this one down here? Yeah, so this line is continuous. Every single little point in between here is considered a solution. And also, it goes forever in that direction and forever in this direction. So therefore, this line has an infinite number of solutions. That's the infinity symbol. You might also write the word infinite solutions. There are infinite solutions in the middle of any 2 points and then also extending both directions. So this is just a summary of what we just talked about. A line, and we mean a straight line, represents all solutions to a linear equation. So all these x, y points are ways that make this equation true. They make the statement work out so that the equivalency is the same. And a line has an infinite number of solution points because it's going in both directions forever. Even if we were to talk about a discrete line that wasn't continuous, had dots instead, it would still go in both directions forever. And then it would still have an infinite number of solution points. So lines have infinite numbers of solutions. Now how about if we have two equations at the same time? Now we said this equation, this is a line, a slope-intercept form, that's going to have an infinite number of solutions. Here's another line, this one's different, has a different slope, different y-intercept. It also has an infinite number of solutions, but they're not necessarily the same ones. So the question we're asking is, do you think we can find a single solution that matches both of these? How would you do that? Well, what if we graphed both on the same set of axes? What would happen? Let's take a look. So here we have an example of that. We have two equations in slope-intercept form. And these two lines graph those two equations. So this one is the purple line. You can see the slope is 1/2. And this one is the green line. The slope is -3. It's going down. So what point is a solution to both equations? So this is all the solutions for the first, that's all the solutions to the second. The place where they cross is right here, and that's going to solve both of them. That point is -2, 1. So that is our solution to these two equations. So we're looking for places where the graphs cross. Now this whole unit is about systems of equations and systems of inequalities. And what we mean by that, we're going to define that now. A system of equations is two equations in two variables that are solved together. And actually it can be more than two. It can be three variables in three equations. Usually the number of equations and the number of variables will match, but not always. It could be 4 equations and 4 variables. It could be 5 equations and 5 variables. We're getting pretty complex now. But in this class, we're not going to get that complicated. We're just going to stick to 2. We're going to do 2 equations and 2 variables. When we get to inequalities, we'll be doing, again, 2 inequalities in 2 variables. So that's what we mean when we're talking about systems. We'll often write them with these little curly brackets like that. And then we'll have an equation here and an equation here. But you might have 3 in there, or you might have more. All right, so this we now know is a system of equations. You can see over here on the right, we've graphed them, and they are both straight lines. Notice this one's not in slope-intercept form, but that's okay. There are other forms that will still graph as a straight line. All we're really concerned about is what point solves both equations. Can we find the single solution to both equations? Can you see it over there on the graph? There it is, the intersection point. That's at 3, 2. The x value is 3, the y value is 2. So the point 3, 2 solves both equations. And then it asks, are there any other solutions for both? Now let's think about this. Here's our first one. Our first one's the purple one. Our second one's the green one. All of our solutions for the first one are here. They follow this line. That line continues. And all of our solutions for the second one are here. This line also continues. So the question really is are these lines ever going to meet again? Is there any other place where they're going to come back together? Well, if we look at the distance between the two lines, you can see that as we get further away from the intersection, that distance gets bigger. That distance is increasing. Or a simpler way to say that is the lines are getting further apart. The further away we move from the intersection, the further apart the lines are. So since the lines are getting further apart, that means they cannot come back together. They can only get further apart. They can only get a bigger distance between them. So no, they're never going to intersect again. There's no other solution. There's only that one single solution in the entire coordinate plane. So if we draw two straight lines on a coordinate plane, how many times will they intersect? What do you think? We just talked about lines that only intersect once, right? So if we draw a line there, and maybe let's get a different color. Draw a line. Oh, I still need my line tool. We draw a line here. Those two lines intersect exactly once at this point right here. Now that didn't fall specifically on integers, that fell kind of in the middle of the square, but that's okay. It still only intersected exactly once. But can you think of a way to draw two lines so that they don't intersect at all? What do you think? Is there a way to do that? Let's see, if I were to just draw a line like this. Oh, not that line. But what if I were to draw another line that went up at the same steepness? Now remember how we talked about the distance between the two lines? The distance between these two lines will be the same everywhere. They don't get closer together, they don't get further apart, they're always the same distance apart. And that is because they have the same slope, the same steepness. They're going up at the exact same rate. So the word we use for lines like this is parallel. They never intersect. They have the same slope and different y-intercepts. So parallel lines, if we were to think of this in terms of systems of equations, this means there's no solution because there's no intersection. No solution to the system because there's no intersection of the lines. All right, so if there's a way to do no answers, no solutions, what about more than one solution? Is there a way to draw two lines so that they intersect more than once? What do you think? Let's come up with a blue there. So I'll draw a line here. And I'm going to draw a pink line now. Let me get pink. There we go. Is there a way to draw a pink line so that it intersects this blue line more than once? Well, we said if they intersect once, they're going to move away from each other. So the only way to really do this is to draw the line right over the top of the other one. You can just barely see that blue one peeking out from under there. They're the exact same line. So now everywhere on this line, every single point on this line, there, every single point will be a solution to both equations, to both lines. So yes, there is a way that they can intersect more than once. It's if they're both the same line. They're right over the top of each other. So just to summarize, let's fill in this table. The number of intersections is the same as the number of solutions. So we have one intersection here. That means we're going to have one solution. These lines are parallel, same distance apart the whole time. So how many solutions here? Well, they don't intersect, so there are 0 solutions. And finally, over here, this is a little bit hard to see, but there's a red line and a blue line right over the top of each other. How many solutions are there here? This will be infinite, an infinite number of solutions, or we could write out the word infinite number of solutions. All right, and then finally, we need to evaluate some solutions to systems. So in this case, we've been given a graph and it says, which of these are solutions to the system? Mark all that apply. Now that second bit is the most important part, mark all that apply. That tells us we may have more than one solution here. So our very first step, the thing we're going to do first is we're going to ask how many solutions exist. Well, let's look at our graph. We have two lines, looks like they intersect once. How many solutions exist when we have one intersection? It's just that one solution, so we only expect to mark 1 point. Which point is that over here? Which point matches that intersection? See, this is an x value of 0, y value of -3. So that's it right there. That is our only answer on this one. Let's try another one. Which of these are solutions to the system? Now we've got two lines. Once again, they're kind of hard to see, but they're right over the top of each other. One is red, one is blue. That's these two equations graphed. Which of these points are solutions? Mark all that apply. So there might be more than one. Let's ask ourselves first, how many solutions exist? Well, that's an answer, those are all solutions. So we have an infinite number of solutions. So many of these might be true. So we need to go through each point and see if it's on that line. Let's look, -1, -4. So x -1, y -4. That one looks to be on the line, so yep, that one's one. -3, 0. Let's see, -3 on the x, 0 on the y. Yep, that's on the line. -2, -2. So -2x, -2y. Also on, man, is this going to be all of them? 2, 1. So this is +2, +1. +2, +1. Now that one is not on the line. That's somewhere else. So this is not a solution. And then no solutions exist. Well, obviously we found 3, so some solutions exist. That's not the answer either. So on this one, the first 3 are our solutions. So to get the problem entirely right, you'd have to mark these 3 and not these 2. Let's try one more of these. Oh, but look, they didn't give us a graph. How can we know if they didn't give us a graph? What are we supposed to do? Well, we have actually many options. Maybe you've learned some in previous classes, maybe not. But we have access to Desmos, right? Desmos is super handy for making graphs when they didn't give us one. So maybe let's give that a try. Let's graph these equations in Desmos. So I've gone out to Desmos. Remember, this is just desmos.com, and you can get to the calculator from there. And I've typed in the equations from our previous slide, from our problem there. And I'm looking at the graph here. Now you can see there are two lines. They look like they're going toward each other, but I can't see where they cross yet. I have to actually pick up the graph and move it a little bit to see where they cross. And then I can actually click on that intersection point, and it will tell me what the coordinates are. Our x value is 3, our y value is -11. That's where they cross. So that is our solution to this problem, 3, -11, and there's only one. So how many solutions exist? One in this case. And the only solution was 3, -11. So that covers today's objective. Given a system of linear equations on a graph, I can correctly choose the total number of solutions, 0, 1, or infinity, and write one solution if it exists in 4 out of 5 problems.